Hello and welcome everyone to this eCognition Deconstructed video. Today we're gonna discuss the multi-resolution segmentation. I would say that's the most widely used segmentation because it creates really nice image objects reflecting the spectral signature of your input image and also delineates your features nicely. So what it does, it creates image objects. It's a bottom-up approach. That means that it starts with small image objects, in this case pixel-sized image objects, and grows into neighboring image objects. You as a user can define the shape and size of the image objects that result from the multi-resolution segmentation. I'm going to discuss that in the next few slides, so pay attention. First, I would like to show you a small animation of how this procedure works. So first of all, the seed looks for its best fitting neighbor for potential merger. That's the rectangle in the middle. So it looks around and checks its neighbors and looks for the best fitting one. So the top one, this green, dark green one, would in this case be the best fitting one for the central image object. If best fitting is not mutual, the best candidate object becomes the new seed object and finds its best fitting partner. So in this case, it's not mutual. So for the new seed, the best fitting neighbor is the one in the top right corner. And now it checks again if it's mutual or not. And that's going to be continued until best fitting is mutual and then the image objects are merged. So in this case, you see these two green ones. Here the connection is mutual, so these are merged. So in each loop, every image object in the image object level will be handled once, and that's gonna continue until no further merger is possible. You as a user can define certain parameters. You see in these green circles the scale parameter on the left hand side. So you can alter this one. You can alter the shape, compactness, and also the layer weights. This is your chance as a user to influence the output of the multi-resolution segmentation. Here we have a few definitions that might be helpful for this video. So first of all, the color heterogeneity. This is the sum of weighted standard deviations for all layers. Shape heterogeneity, on the other hand, is the deviation from a compact or a smooth shape. The compactness is the border length divided by the area, whereas smoothness is the border length divided by border length of a bounding box. So just keep that in mind, or you also can go back in the video to check these definitions. We're gonna continue on the main settings that influence the size and shape of objects. So we have scale parameter, shape, and compactness. First of all, the scale parameter. This is a homogeneity criterion and is a combination of the spectral and shape criteria. And that means that if you increase your scale parameter, your image objects become more heterogeneous. Therefore, a higher scale parameter means you have higher variability of pixel values within your object. To put it in a nutshell, if you increase the scale parameter, the size of your image objects will increase as well. So the question always pops up, what scale parameter is best? And there is no definite answer to that question. It depends on a lot of different things. For example, the sensor type that they're using, the purpose of your segmentation, additional input information, your objects of interest, and also your expert opinion. So it's very difficult to come up with one number that reflects the best scale parameter for your segmentation. Nevertheless, you're gonna find a tool called ESP tool to estimate the scale parameter in the eCognition community. Usually it's trial and error, so play with the data and test different options, and it's your experience. So use it and you're gonna know which settings are best suited for your purpose. Just some personal recommendations. I personally create multiple multi-resolution segmentations within one project. One focusing on extracting buildings, for example, so I adjust the parameters for that segmentation. A second one for extracting trees. A third one for water. So I always create specific segmentations for each class I want to classify and extract. The recommendation would be to do class-specific segmentation and use class-specific segmentation parameters and algorithms and combine afterwards your results. A final personal recommendation regarding the creation of image objects is that the objects should be as large as possible, but should still nicely delineate your objects of interest. So that means that I try to generate a segmentation that nicely delineates every distinct object of interest. Let's have a look at an example. This would be the input image, and always remember, right? Initial image objects are your building blocks. So we have a lot of tools to alter the outline of your image objects. I'm increasing my scale parameter, and this leads to larger image objects. And it depends on your purpose. These image objects, for example, would not be good if you are looking for single cars, but it's a good segmentation if you're looking for the roof of the building. Even larger scale parameter results in very large image objects that are more or less meaningless in this case if you're looking for building or cars, because they're covering all of the features in one image object. Let's continue with the shape setting. So you can alter this parameter as well. The high shape value leads to low color influence, which is the spectral reflectance. So if you increase the shape, the influence of the color homogeneity criterion is reduced. On the right hand side, you see if you increase it, the shape influence from 0.1 to 0.3, the color influence is reduced because these two make up the value of 1. The minimum value is 0.1, maximum 0.9 for the shape. Changing the shape value is going to change the result of your multi-resolution segmentation. The same holds true for the compactness. However, the compactness is influencing the shape, and that makes it pretty difficult for me to explain. Nevertheless, I tried to put it into this graph on the right hand side, so you see that the compactness and smoothness make up the value of 1. So compactness plus smoothness is 1. What you can change is the compactness, not the smoothness. The smoothness is automatically adjusted, so if you increase compactness, smoothness is lowered. And this relationship is influencing the shape. So if you have a high shape value and a high compactness value, the shape will have a high influence onto the segmentation results. So you're going to get really compact image objects. If you increase the shape but have a low compactness value, you're going to get more smooth image objects. But keep in mind that then the spectral signature, if you have a high shape value, the spectral signature is considered less in the segmentation procedure. Another input that you can alter is the layer weight. So you can define different layers that are included in the segmentation, and also can weight them. So you can weight them 0, so they're not included in the segmentation, or you can weight them even higher. For example, if you're doing a segmentation within a water area, and you might say, all right, the near infrared is very important, or it's a nice discriminator between water and non-water. You simply can increase the weight of this layer, and then your results look better. That was a pile of information, and that's why we're looking at use cases in eCognition. So we're looking at a subset of a city in the US. Maybe you know where we are. And I'm just simply going to execute a few multi-resolution segmentation. This is the default setting, so we're choosing the algorithm multi-resolution segmentation. Leave everything default, so you see on the right hand side the parameters, the scale parameter, shape, compactness, and so on. Simply going to execute that one, and let's see how the results look like. I also depicted here on the right window in the image object information window the number of objects and also the average area of an object. That's the result. So you see we have large image objects where we have fairly homogeneous reflectances. So in water areas and also in this grass area, and where we have a more heterogeneous section of the image, like in the city, buildings, trees and stuff like that, you end up with smaller image objects using the multi-resolution segmentation. And you also see that spectral similar areas are segmented into one image object. So that's very nice to have. Let's simply increase the scale parameter to 420. So instead of 42, we're increasing it to 420, and the result's going to be displayed at the bottom. And you're instantly going to see that we have way larger image objects because we increase the scale parameter. We also just have 222 image objects in this case. The top one has a lot more. And you see nicely that we have, for example, for this building, using 42 as scale parameter, a lot of image objects within the building. Using 420, it's just 2 or 3 image objects. And a big difference is also here in the river. It's just 1 image object here, whereas we have multiple using 42. But you also lose small features. So you see these boats in the river, they're visible or they're segmented in using 42 as scale parameter, and they are merged into the surroundings using 420. So it depends on what you want. If you look for boats, I would go for 42. If you look for rivers, you also could go for 420. Now I increase the scale parameter to 1000, and you're gonna see in the bottom pane the number of image objects is reduced to now 31. And these image objects are pretty large and are covering different spectral features like trees, grassland, also background and buildings. So they are included into one image object. In some cases that might make sense, but if you're looking for single buildings, this would be too big, and also you wouldn't be able to detect the boats. Okay. Let's change the compactness and the influence of shape. So I increase this to the maximum so you see the difference and the influence of these settings. So we're again looking at scale parameter 42 on both panes, top and bottom, but I increased shape and compactness for the bottom one to the maximum value of 0.9. And you see that we have very compact image objects. That's a nice example here, this area. If you increase shape and compactness, you see you get compact image objects, but they also covering different spectral signatures. So I don't know if you're interested in this. Having this might make classification difficult because you have trees and grassland in one image object. But again, it depends on the purpose of your classification. And that's the last thing I want to show. Thank you very much for watching. I hope the multi-resolution segmentation became a bit more clear. Have a good day and see you next time.